So moving on into our critical angles and our pulley forces. So a captain friend of mine that works here, Captain Robertson, put it pretty well. He said that when you're really thinking about all of the rules of the game in technical rescue, the main thing you need to think about is, do you have a good anchor? Do you have that anchorage set up? Do you have a main and a belay? And the belay is going to actually decrease the chance of that plummet fall, meaning that they're not sharing the same high point, that belay line will do its job, and that you have the right equipment on your rescuer and the right amount of equipment with that victim harness or whatever you're going to need to perform the rescue. Those are the main steps. But when building these systems, we do have to think about critical angles and pulley forces. And pulley forces and critical angles, sometimes you get mixed in because they're using the same numbers, like 60 degrees, 90 degrees, 120 degrees, but we're talking about them in different ways. So we'll go over pulley forces first. So if you have a pulley and it's on an anchor and you have a rope that comes up and through that pulley and straight down at a 0-degree angle, this force that's being applied to this anchor will be 2 times the load. 2 times the load. Why is that important? When we build mechanical advantage, you have 1 unit of force coming in and 1 unit of force coming out. We know that that would make this, if this was our load and not our anchor, we know this would be a 2-to-1 system because 2 ropes are being pulled at the same time, suspending or applying force to this point. If we took this and made it more of a 90-degree angle, it's going to be 1.5 times the force at this point. And then if we went even more obtuse to 120 degrees, this is where you're going to see 1 times the load or force on this point of the system. Mainly, as you start adding pulleys and stacking pulleys onto your system, you notice that they're all at 0-degree angles. Start thinking of that multiplication force. Hey, I got 200 pounds on the end of the line, 300 pounds on the end of the line, but I got 3 pulleys stacked here making 90-degree angles. That's where you're going to start seeing that force multiplier. And so it's not, this anchor is not feeling 300 pounds. Rather, it's feeling 900 pounds of force. So this is where pulley forces come into play. It's still the angles of 0 all the way up to 120 degrees, which we're going to talk about with critical angles, which is more your high lines or your anchor, multifocal point anchors. But specifically with pulleys, this is what we're looking at. So where it's applicable is when you're building the mechanical advantage. If this is something you want to have 2 times the force on, that's good. Other things to think about is if you're using a natural high point, like a tree limb, something to consider would be, how much force am I putting on that tree limb? Or if you're using Arizona vortex, how much force is being applied down into the legs? Can my soil handle that? Am I too close to the edge? Can the edge handle that much force? Can the top of this system handle the force? So those are some things to consider when looking at your pulley forces. When we're talking about critical angles, it's really going to be the inverse of the pulley forces, and we're going to be talking about this specifically with like a multifocal point anchor. So if you're going to be having a self-adjusting anchor, or you need 2 different anchor points to come together for your system, the angle we're talking about is going to be that interior angle. At 120 degrees, and this is your load, at 120 degrees, each of these anchors is seeing 100% of the load. This is going to be okay to operate, but not optimal. This is as far as we want to go. This is as obtuse as we want to go on this angle. If you do go more obtuse, and let's say we go to 150 degrees with your anchor strap, which is easy to do. You tie it, maybe you had short webbing, it's just you tied it already and you're in a rush and you're like, God, it should be fine. But again, if we start going to angles like this, 150 degrees or greater, understand that these are force multipliers. At 150 degrees, each of these anchors is seeing 200% of the weight of the load. And this will go all the way up to where if you tried to do a straight line across at 180 degrees, each one of these anchors would see 11 times the load. So why is that? Why does that happen? If you took 100 pounds and you suspended it here on the end of the rope, say this was a piece of rope and you hold it, you got 100 pounds in your hand, it's not moving, that's all the force that you're feeling. But if you suspend this rope across and you pull it tight enough, it has so much tension that it's using, so much force that it's using to hold that rope straight. And then you try to add that 100 pounds in the middle, it's now, both of these anchors are still trying to keep that straight line, and you've applied that force in the middle. And so not only is it trying to keep this line straight and now magnifying the force, but now you added more workload for it to try to do that job. If it can't move, this 100 pounds of that you've now suspended in the middle of the rope is actually going to be 1,100 pounds at each anchor. When building high lines, when you get into rope rescue technician, if you go out on a RIMS assignment and you're building these lines, this is an absolute fail point for your system. Now in your head, you're going to go, well, I like it straight across. I need to navigate the edge, navigate the water, navigate the terrain. It looks good in your head to keep this as tight as possible. Realistically, even on your high lines, you want to see no more than that 120 degree angle for your carriage that's going to be going across on these lines. We sometimes use load cells to actually calculate no more than 600 pounds on those tensioning lines. But the same thing is true with a lesser complex system where we're just trying to capture two anchors with webbing or rope, and we're building a multifocal point anchor. We want to be less than 120 degrees. If we get this out to 90 degrees, at 90 degrees, I believe it's like 71% per anchor. And then even more so, if you get to like 60 degrees, you get down to that 50-50 load sharing and so on and so forth.
Question for you.
Yeah.
On the top one there, the 180,
yeah,
we're doing there, does that cause increased tension on the rope as well, or just the anchor points?
The anchor points. The rope is suspending it, but it isn't under tension. This line or this webbing or anchorage that you've created between these two anchor points is already under so much tension to keep the slack out of it that when you apply this force in the middle, it's going to multiply that. So if we stood side by side and we were trying to hold the rope as hard as we can, imagine just pulling, and then we put a weight in the middle of it, more than likely it's going to bring us both forward because it's going to be such a multiplier. I don't have the exact physics down to why it happens, but it is something to take into consideration. All that to be said, big takeaway. If you're going to share multiple anchors, the interior angle should be no more than 120 degrees with a goal of 60 to 90 degrees or less than 60 if you can. But of course, it does come to a point where you're going to be so far away from your anchors, you might not have that much room going past your up to your edge. So, and again, this is going to all kind of tie into the next topic, which is what is low angle, what's steep angle, what's high angle, what type of systems can we use certain anchors for, when can we forego using a belay line, things like that. So pulley forces, critical angles. These are going to be your critical angles. Specifically, critical angles are being used when you're deflecting lines, when you are creating high line systems, and when you're just capturing multiple anchors to make one bomb-proof anchor.